Hi, everybody. It's Professor Mitchell. We're continuing with 3-2, measures of variation. So this is called the empirical rule for data with a bell-shaped distribution. So this is what we call a normal distribution. So if you have one of these distributions that's called normal or bell-shaped, somebody figured out that you have these properties. About 68% of all the values in the data set fall within one standard deviation of the mean. And I think we talked last time about what that means, within one standard deviation of the mean. So let's say the mean was 100 and the standard deviation was 20. Within one standard deviation would mean 100 plus or minus 20. It would mean between 80 and 120. Okay, about 68% of the values would fall in that range. If you go out to 2 standard deviations, then you get about 95% of your data. Okay, so again, if the mean was 100 and the standard deviation was 20, now we're talking between 60 and 140. All right, so 60 comes from 100 minus 40, 100 minus 2 times 20, and the 140 comes from 100 plus 2 times 20. And then almost all of your data falls within 3 standard deviations of the mean, 99.7%. Okay, so it's really, really unusual to find anything that's more than 3 standard deviations away from the mean. Okay. All right, so I think we're coming up to a point here where I added a little something because they just kind of handed you this thing. All right, so this was something I added. I'm used to doing this in a class where I write a lot more on the board. Okay, so the question is, what percentage of the data lies between each pair of dashed lines? You see these dashed lines at the bottom, and there's your bell-shaped distribution. And as a reminder, on these 3 bullets, here's what the empirical rule says. I thought it would be helpful to have that up on the same screen. So let's start with the first bullet. 68% of the values fall within 1 standard deviation of the mean. So this is another one of those times I'm hoping that people watching the video can see my mouse pointer. All right. So I'm talking between here, this is 1 standard deviation below the mean, and over here is 1 standard deviation above the mean. So you have these 2 regions that are mirror images of each other. Remember, these bell-shaped distributions are symmetrical. So if I'm telling you that there's a total of 68% in this region right here, then hopefully it makes sense that within each one of these regions separately, there would be 34%. Okay, half of the 68%. Okay. All right, so now let's go to 95% of all values fall within 2 standard deviations. So that would be, oh, I just noticed there are no dashed lines over here. They're supposed to be. All right. Well, let's see here. Would it be too much trouble to throw one in there? Let me get my, just grab this. Okay, so put a little dashed line right there. Okay. Well, at least this way, if you can't see my mouse pointer, at least you know where I'm looking. All right. Okay, so 95% is between here and here. But we've already accounted for 68%, right? So in these 2 regions here and here, there's going to have to be the remainder of that 95%. So we're talking 95 minus the 68% that I already have. Comes out to 27%, right? So that 27% needs to be divided equally between here and here. So hopefully it makes sense that within each one of those regions there would be 13.5%. Right? Okay, and then I do the same thing for these last little regions here. And then once I hit the 99.7%, I'm not going to worry about what's outside. You know, that remaining 0.3%, we don't really think about that too much. So you would do the same thing. You would do 99.7 minus 95, right? I've already accounted for 95%. And so there's 4.7% left. That's going to leave 2.35% here and 2.35% there. All right, so this is basically the same picture we just made. They've just made the percentages a little more exact. So the 68, 95, 99.7, those are kind of rounded. But if you're doing a problem where you have to use the empirical rule, it's perfectly fine to use the rounded off numbers that we just came up with. All right, so here's an example. IQ scores, it's kind of an outdated example. People don't talk about IQs too much anymore. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. So they want to know what percentage of IQ scores are between 70 and 130. So what we have to figure out is how many standard deviations above and below the mean are 70 and 130. Oops, okay. All right, well, in the very next section, we're going to talk about z-scores. And I think z-scores kind of make this problem a little easier. But in the meantime, they're just pointing out that 70 is exactly 2 standard deviations below the mean because the standard deviation is 15. So 2 times the standard deviation would be 30. Okay, so if you do 100 minus 30, there's your 70. And if you do 100 plus 30, you get 130. In any empirical rule problem, they will give you numbers that are a nice round number of standard deviations above or below. It will be something like 2 or 3 or 1. All right, it'll be one of those things. Really can't do anything else other than 1, 2, or 3 standard deviations away. So as soon as you figure out that 70 and 130 are 2 standard deviations away from the mean, I go to my empirical rule, which says that that catches 95% of the data. 95% of the data are within 2 standard deviations of the mean. Okay, so Chebyshev's theorem is kind of similar to the empirical rule. It tells you how much of your data can you expect to find in a certain range. The difference with Chebyshev's theorem is that it can be used with absolutely any distribution, does not have to be bell-shaped. Okay. Now the trade-off is that Chebyshev's theorem is a lot less specific than the empirical rule. The empirical rule is very exact, right? It says within 1 standard deviation, 68%. Within 2 standard deviations, 95%. So if I don't know what kind of distribution I'm looking at, the only thing I can do is say at least. There's going to be at least this much. So the way that they say this, it's kind of weird until you start filling in specific numbers. The proportion of any set of data lying within k standard deviations, so k is some mystery number, of the mean is always at least this proportion of the data, 1 minus 1 over k squared. And the best way to understand this is to look at examples. So for example, if k is 2, then 1 minus 1 over k squared turns into 1 minus 1 over 2 squared, which is 1 minus 1/4. That's how they get 3/4. So at least 75% of the data lies within 2 standard deviations. If your distribution is bell-shaped, that number becomes 95%. All right, but this just says at least 75%. So that's a lot less specific, right? And if you put in k equals 3, This turns into 1 minus 1 over 3 squared, which is 1 minus 1/9. 1 minus 1/9 is 8/9. So within 3 standard deviations, I guarantee you in any distribution, I don't care what its shape is, you're going to find at least 89% of your values. And again, if your distribution happens to be bell-shaped, that number turns into 99.7%, almost all of it. But I guarantee at least 89%. So here's an example of using Chebyshev's theorem. If, again, IQ scores have a mean of 100 and a standard deviation of 15, what can we conclude from Chebyshev's theorem? Very open-ended question. Well, again, using k equals 2, k equals 3, you can reach these conclusions. At least 3/4 or 75% of your IQ scores would be within 2 standard deviations of the mean. And if your mean is 100 and your standard deviation is 15, that turns into between 70 and 130. And if you put k equals 3 into Chebyshev's theorem, you get at least 89% of IQ scores are within 3 standard deviations, which would be between 55 and 145. The only thing that I don't really like about this example is that IQ scores are bell-shaped. All right, so you can get a much better answer out of the empirical rule. All right, they're just using this as an example. Okay, the last thing I believe in section 3.2 is called coefficient of variation. The coefficient of variation is good for comparing 2 different samples or populations that have different means and or different standard deviations. So what this does, because remember the standard deviation is expressed in the same units as the mean. So for example, if the mean is in inches, the standard deviation is also going to be in inches. So it expresses the standard deviation as a percentage of the mean, okay? Which again is good if you're comparing different samples or different populations. So here's how you do that. If you're dealing with a sample, you just do, well, either way, you do the standard deviation divided by the mean, and then multiplying it by 100 just changes it from a decimal to a percentage. That's all that does. Okay. All right, so I made up this silly little word problem. Here's the round off rule for coefficient of variation. Round it to 1 decimal place and write it as a percentage. Okay, so the example is in Mitchell's class, exam scores out of 100 points have a mean of 76 and a standard deviation of 19. By the way, this is completely made up. In Dawson's class, in Professor Dawson's class, Dr. Dawson, exam scores out of 200 points have a mean of 160 and a standard deviation of 48. So let's say that I was trying to compare the amount of variation in my class versus Professor Dawson's. That's kind of difficult to do just by looking at these numbers. But if I calculate the coefficient of variation, what I find is that my coefficient of variation is 25%, which means that my standard deviation is 25% of my mean. Professor Dawson's standard deviation is 30% of her mean. So that means that in Professor Dawson's class, there is just a little bit more variation than there is in my class. Okay, so we end with just this note, which is not for everybody. This is probably, more than most people need to know. They're pointing out that the sample standard deviation is what's called a biased estimator of the population standard deviation. And what that means is that values of the sample standard deviation do not tend to center around the value of the population standard deviation. Okay? However, interestingly, the sample variance is an unbiased estimator. okay? Variance of samples do tend to center around the value of the variance of the population, okay? Which is nice because then you're not overestimating or underestimating the population variance. And that finally is the end of section 3-2.